We are live. Good morning, good afternoon, good evening, wherever you are in the world. You have reached Saturday Science Chats. Hey, this is David D. Hilscher, and I'm with the John Chappell Natural Philosophy Society and, of course, Dissident Science. And today we are going to be having a first in a part one of a part three series. And this is continuing our evolving perspectives on the history of science. And this one is time and physics, something that if you love physics and cosmology and science in general, it's almost impossible for you not have to have thought about what time is. And of course, we've got one of the foremost experts on the planet Earth, at least we say planet Earth, Nick Percival, who's here. It's going to be just great. I love Nick, and we'll talk about that coming up. But at first, I want to congratulate you for even tuning in, because if you are watching this, that means you are a person who is a critical thinker. See my t-shirt right here? Critical thinking is very important. And as Aristotle or someone else has said, because I've been told that maybe Aristotle didn't say this, but hey, it's fun anyways. It's a great saying, and that is, it's a mark of an educated mind to be able to entertain a thought without accepting it. And by the way, if you are watching this intro and you want to get to Nick right away, just fast forward, because this is recorded. Go forward and start his lecture. But this is for those people who haven't been here before. So again, you have that option always when you are watching this recorded. And please like and subscribe. It is very important to us, because that's how we get more and more people who are watching this channel and more subscribers. In fact, we have over, I want to thank my Dissident Science subscribers, coming up to 4,100, coming up to 1,000, still inching our way up there with the John Chappell Natural Philosophy Society. And so we're really want to thank each and every one, and congrats for watching this, because this is a place where you're going to hear critical thinking. And also a couple other things I'm putting here. And there's, you got to remember, folks, we're all in this together. I know a lot of times we have people, even in the chat, who are just like attacking. It's like, folks, we have to all remember that let's fight the illogical mainstream science and not ourselves. Support your fellow critical thinker. Even if you don't agree with them, at least agree to say, hey, people are going out on a limb to write a book or to talk about something, or thought many years, as Nick has, on time. So guys and gals, please just, remember the big picture here. And also, the other thing I want you to try to remember, and this is not easy either. So you know me, I am the physics police, so I'm going to get right on your case. And we are all wrong, every one of us, all of us. And the way my dad has put it, I'll quote him whether he wants to be quoted or not, or I'll just give him the quote. But basically, some ideas are less wrong than others. That's pretty much what we do as human beings. This idea that everything is absolute, everything is understood. Yeah, we have a lot of things like, the atomic structures. We understand a lot about that, but we don't even know really what's going on as much as we think we do. But I think the other thing is too, when we dissident scientists have our own ideas. You're an etherist, or you believe in a lattice, or we have our particle model, for instance, or you have a new way that atomic structure works. Please remember, just don't fall in love with it, because the moment someone comes up to you with a legitimate criticism, you're going to be looking really silly if you really don't do that as a habit in general, to realize that, yeah, these are neat ideas, these are great ideas, but they're all wrong, just less wrong. Welcome. Hey, good morning, Richard Jesh from Berkeley. Thanks for tuning in. And again, thanks to everybody tuning in live here. All right, let's keep going. And of course, our mission is to promote critical thinking without malice, meaning you can publish, and we help publish, promote scientific work outside of mainstream in mathematics, cosmology, physics, etc. We provide a forum to discuss and present serious papers and theories without fear of censorship, and we are completely run by our members. We do have websites, and you should check them out. If you can fast forward to the main event here, but if not, it's your first time here, you can go to beyondmainstream.org. If you have no idea that mainstream science is a lot bigger mess than you think. In fact, we're in model crisis, is what I call it right now, in the Kuhnian terms, and you can check it out there. And it's like a magazine, so you can read. It's really cool. You can learn about all the people and the great critical thinkers out there, including Nick's on there, and all kinds of articles that are very interesting. Also, our community, naturalphilosophy.org, critical thinking community. It's very active lately, which is great. We have software for that, and really great software we're using, Buddy Boss, I think it's called. And so that's really a lot of fun, easy to participate. We have lots of groups and discussions going on there. You can see them. And of course, we have our Wikipedia with over 10,000 pages to check out. Now, I'm going to, let me get out of here. I want to show you guys what's going on. Don't save. There you go. This is our website for our community. You can see here that, there, my dad posted a new video this morning. Here is the video for today, but you can see here people discussing things, sort of like almost like Facebook. And again, we pay subscription to this. It's really great software, and you can see these are groups over here, kinds of groups, and here are the people. You can subscribe to our newsletter. There are some of the people there who we've been discussing lately, and all the different groups that you can join in. You can have your own profile there and everything. For instance, here you can see my profile. Each person has that, and you can go there and find out what they're saying, blog articles, etc. So you do want to check that out. It's a lot of fun, and if you are really into discussing and meeting other people, it's really great. I thought I'd show that to you today. And also very, very important, and I really do appreciate it because I see people joining newly almost every week. We do live off of our memberships and our donations. We have monthly memberships, and and we also have annual memberships, and we do get donations from people, generous donations. We have about $2,300 a year for everything from this platform you're watching now to that website you saw, the server for the website. This is all publicly. It's owned by the members who do help out, and we need your help. We barely get by, and that's okay. But if you can spare $5 a month, that would be great. If not, $35 a year. It helps every person. If they give a little, it's going to mean a lot to us. I want to thank our patrons. Nick Percival is one of them. He's going to be speaking today. He's been a patron. I want to greatly thank him for his generous givings to our group. Dr. Cynthia Whitney as well. Ramsey Penname, and of course all of our annual and monthly memberships. And we need your vital support. And the optimal word there is vital. Vital means life and death. Life keeps us alive. So that's really important. So please, coming soon, next week is going to be really great, as well as many other things are coming. We already have things lined up. Next week, we will be here 3 hours later. So if you're on the East Coast, we'll start at 1. If you're on the West Coast, it'll start at 10 a.m., which is really great. And if you are in Hawaii, like Tao Lin, take a look him up. Tao Lin, author, pretty well known. He's been written up in magazines in New York City and London. Really a great guy. He has also written papers about alternative models, and he actually watches this. So if you're out there, Talin, it's great to have you as a patron watching this. Keep critically thinking. And of course, Nick Percival will be having Special Relativity time, actually talk too. I probably it doesn't matter. It's about time and special relativity. He's going to have 3 talks altogether. My dad's going to be coming back talking about the physicality of parallel resistors, diodes, and transistors, how he as an electrical engineer has really embraced and gotten to understand what possible models could be made for the physicality of electronic components. We use them all the time, but all we have are empirical equations that have nothing to do with reality. And I put this down here because I know I'm just going to get slings and arrows from everybody for even saying this. But yep, I am going to host a great debate, and I'm going to be on the ether doesn't exist side, and I'm welcoming anybody who wants to debate me on that. Again, a very cordial debate. Okay, I'm going to tell you, I cannot say that ether for sure doesn't exist. I don't think it's a good model. I think there's too many flaws with it. But does it exist? It could. That's the way you have to have an attitude. If I was a betting man, no. I think there's a better model out there. That's okay. But we're going to debate it. And I'd love, if you are interested in being on the other side of that debate, then contact me. And of course, Ian Cohen is to blame for this. So if you don't like that, especially after we do it and you don't like it, I will give you his email address so you can send it to him. But anyways, great guy. It was a great suggestion. So I'm going to put that one out there because I'm ready for that one. I've got a couple arguments that I think are going to be fun to look at. But again, we're also going to be doing debates on other things. So if you're interested in that kind of format, contact me, and we'll go forward. But we're going to now get to our main event here today, which is on our series of what we call Evolving Perspectives on the History of Science. Now, let me explain a little bit about this. Nick was very helpful in this, as were a couple other people. And what that really means is we critical thinkers, people like myself and Nick and Ian and my dad and many hundreds of people, thousands of people around the world who've been looking as critical thinkers, mainstream science, really realizing all the problems. We've been looking at this for many years, and we end up developing a different perspective of history. That is, when we go and look at Einstein's relativity, for instance, we don't look at it like mainstream does, saying that was a paradigm shift. To me, that was actually a model shift and a start of what is a crisis in science. To me and many dissidents, relativity started a crisis in science. It wasn't a paradigm shift because it's got more problems than it supposedly answers. So again, that's what this is about. That is, we critical thinkers, when we look at history, the history of light, the history of gravity, the history of time, we look at it a lot differently, in my opinion, in a more objective way, because we're not afraid to say everybody's wrong. We're just maybe less wrong than before. And so in this same vein, we're going to be talking about time and physics, something that this man has looked at for many years. But let's talk about him, give you a little bit of his background. He is Nick Percival's American scientist and entrepreneur who is best known for his work criticizing and explaining Einstein's theory of relativity's treatment of time. So that's why you can imagine. Nick graduated from Harvard with a degree in physics. So there you go. On one of the criticisms we get is like, you don't have a degree, you have to go to school. What they really say is you've got to be schooled in the way we think, and then you won't be so critical, which is terrible. It's like the opposite of what universities should do. He has spent more than 50 years focusing on the twin paradox, and from those studies has come to know the many problems with special relativity, and also about time, of course. I put these together here. As an entrepreneur, Nick started several companies in the late 1990s when the internet was really just starting. He co-founded TeacherWeb at that time, goal providing teachers and educators as an easy way to create and update websites for communicating with students and parents. Yep. And of course, I did this for you, Nick. He has a YouTube channel with amazing videos. If you haven't checked it out, you should. He calls it the Nick of Time, which I think is obviously very clever. And you can get there. You don't know how to get there? Well, I made it easy for everybody. You just got to go to nick.naturalphilosophy.org. That is, if you go to type that in any browser, that'll get you to this YouTube channel with Nick, and he's going to have these videos will be available after today. So you want to definitely check that out. So I'm going to bring up our guests for today before he gives his presentation. And everybody, welcome Nick Percival. How are you doing?
Pretty good. I look a lot different than that picture that
me
before.
Too. Look at me. No, but you still, your face is absolutely recognizable, and you just look more wise. We just, that's not a problem. So tell me, tell the audience who don't know you at all, how did you get involved with the idea of time and even caring about it? Most people don't want to give time any time at all. Maybe give us, give the person a background why you came into it. I think that's really important.
Well, at Harvard, I took a course on special relativity, and then I saw in Life magazine it said that because of special relativity's time dilation, the astronauts would come back to the Earth younger. I didn't dispute that they would come back younger, but um, special relativity actually didn't predict that. So I brought that attention to my professor, and I thought we had come to an understanding. Uh, Incidentally, when I was taught special relativity, I saw that flaw, without thinking about it, and thought that he was talking about a more sensible theory. Anyways, I left the academic physics world, but have remained having physics as a hobby.
So you left it. Were you thinking about going into it, or were you
Yes, I
discouraged?
was thinking about going into it. Yeah.
Wow. So you were discouraged by very early its irrationality, or
Well, and also I was intrigued by computers, and I went in like you. I went into computers and software
right,
development. Yeah.
right. Okay. Well, why don't you tell us a little bit about first of all your series, and then second of all, just give us a brief introduction what we'll see today in part one here.
Okay, I don't have a total theory of my own. I just focused on both from a logical point of view. Special relativity cannot be describing the physical world and what's happening physically, and that's what physics is supposed to be about. Um, and I sort of realized that, despite my conversation with the physics professor that I talked about earlier, that gee, the academic physicists have this crazy interpretation of special relativity, at least part of the time. Sometimes they shift to a totally different interpretation. So I thought that was important. I kept working on it and working on it, and then eventually I discovered the NPA, which evolved into the CNPS, and it was great to have a lot of other people who thought the same way.
So when did you join the MPA? Do you remember?
Um, yeah, Greg Volk brought me in
Oh,
maybe around. I actually don't remember. It's 10 years anyway,
right, right. So it's
and
not too long,
back in the
right?
NPA days.
Right. So you weren't there from the beginning, though.
Not from the beginning, no, no.
Right, right. Okay. All right. So tell us a little bit about what we're going to see today.
Okay, I've um, it's a relatively short video, only 45 minutes. I give an intro, so I've covered most of the details. I'll just add a couple of thoughts. One, the charts, the title line has a number on it. That number is basically, for me, you'll find that they don't go in sequence and there are gaps between them. But you can use that number as a shorthand to ask a question, like on chart 15, bullet 3, I have this question, and that will help me. Um, Also, this first presentation is a little bit mundane, at least for some of the CNPS listeners, but it provides the conceptual base for truly understanding parts 2 and 3. To me, this is just one long presentation, and the whole makes sense together. So just focus on what's happening conceptually. If I give the wrong date for something or left out one of the scientists in the past couple thousand years, uh, don't bring that up in the Q&A because I don't want to distract other people.
Right.
I want to keep in mind what the key concepts are that we're going to carry on to part 2.
Okay.
And
That's really
with that,
great.
we can go to the video.
Okay. Well, here's the video, and we will get it started.
Welcome. The topic is the past, present, future of time in physics. That's a very broad and sweeping topic and couldn't be covered in one presentation. So this is part one, where we will look at the history of time in physics. Part one happens to be a redo of a talk that I gave to the CMPS back in 2014, and is also talk number 29 in my Nick of Time YouTube channel, giving a series of 33 talks on time and physics. So we're going to look at the history of time in physics through the millennia. And we're not going to look at those debates from the philosophers about time, as those debates were much too vague and could not come up with a concrete enough construct to use in a physics model. So we're not only going to talk about the history of time in physics, but the perspective will be from a mainstream physicist, namely Professor Lee Smolin, who also is really giving the consensus opinion about the history of time in physics. And we'll end up with a high-level conceptual discussion of special relativity and general relativity's view of time. And then in part two, where we talk about the present of time in physics, we will delve into that topic on relativity a lot more deeply, including the evolution from 19th century physics to Einstein's paper in 1905. And that should be extremely insightful and give you much greater understanding of relativity. Since much of this talk will be based on Professor Lee Smolin's ideas, we need to know more about him, including his biases, etc. He's a highly respected mainstream physics professor in academia who loves relativity. In addition, he's also a critical thinker. He wrote a book criticizing string theory as being too much math fantasy and not enough hard physics. He also wrote the book Time Reborn, which is an excellent book that I recommend to all, and it's the basis for this first talk. We'll start off with a summary of that book. The main thesis is that the concept of time has been slowly removed from physics. Einstein claimed that the distinction between past, present, and future is only a stubbornly persistent illusion. And that thought is certainly contained in both special and general relativity. So this removal of time from physics, the peak to date anyways, is in relativity. So Lee recommends that time needs to be put back into physics, and especially for cosmology and quantum gravity. Lee starts off by describing ancient intuitive views. Now, if one's standing on the Earth, one has no sense that the Earth is rotating about its axis or orbiting around the sun, so the intuitive concept is the Earth is at rest, and that people are at rest, except when they're walking and moving with respect to the Earth's surface. So their view was that not only common everyday humans, but the scientists and physicists of the time, the concept was that the sun, the moon, the planets, and stars all moved with respect to the stationary Earth. Also, and this is quite important, that the passage of time was defined in terms of those motions or those astronomical processes. The day was thought to be the time, naively thought to be the time, that the sun makes a full rotation around the Earth, whereas in reality, it's really that the Earth is making one rotation about its axis. And the week is 7 rotations about the Earth's axis, and an hour is 1/24th of the time it takes for the Earth to rotate once around its axis. And even the month is approximately it corresponds to the moon going through its various phases. In addition, the ancients thought of there being 2 separate worlds. The celestial realm was unchanging and had perfect repeating patterns, versus the realm of the imperfect, chaotic Earth. They consider them 2 quite different, separate realms. Here's a picture of that ancient view with the Earth at the center and all the celestial bodies going in perfect circles around the Earth, including the moon, the sun, all the planets, and all the stars. And to the degree that the precision of their observation of the time, it worked out pretty well. So that's the picture of Ptolemaic astronomy. And Lee makes the point regarding that and geocentrism is there's a lesson here, which is that neither mathematical beauty nor agreement with experiment can guarantee that the ideas a theory is based on bear the slightest relation to reality. I would contend that regarding relativity, that lesson was completely ignored by Lee, as we'll discuss later on. So the Ptolemaic view continued to evolve, like science is always evolving. Sometimes it goes down the wrong path even, but it's always changing. So the view was that the heavenly bodies always moved in perfect circles around the Earth. But then they found that there were some retrograde motion, so that nice simple picture became more complex as they had to add 55 circles to take into account retrograde motion. But they were still stuck on circles because that was considered the perfect symmetric shape. Then Tycho Brahe came along and made another step forward. He said that the planets travel around the sun, and that yielded a much simpler picture. But because his belief in the Earth-centered view was still strong, he couldn't make that next step. So he said that, well, the sun still moves around the Earth. He assigned Kepler to analyze the orbit of Mars, and Kepler, doing careful work, saw that that orbit was really an elliptical orbit and not a circular orbit. And he made a great jump and change in paradigm and saw that the Earth was also moving around the sun. Now everything, all the planets were moving around the sun. So that really was quite a major change in astronomy, a paradigm change. But it also was a great change in terms of time, in terms of the underlying model of time, because in the geocentric view, a day was the sun making one revolution around the Earth. But the true physics was that the underlying motion, the underlying process of the day was the Earth making one revolution about its axis. Okay, having covered a couple of thousand years of physics, we come to Galileo, and he was the first one to discover that the motion of all thrown objects follows a simple type of math curve, a simple geometric object. The parabola, the math definition is that it's the loci of points that are equidistant from a specific point and a specific line. And the equation is simply y equals x squared. It's a static equation describing the entire parabola at once, and there's no t for time in there. So at least scientists now are beginning to apply and see patterns in what happens in the realm of the Earth, not just celestial objects. So, back in the days of the Ptolemaic picture, we had everything orbiting in circles, and then we advanced to seeing the orbits as ellipses, and now we have Galileo introducing a parabola to describe thrown objects. But all of those pictures are static in the sense that they show the entire motion or process as all at once. So Lee's point is that physics was really treating a dynamic process as a static math object, where these geometric objects give a static picture of the whole phenomenon at once, and the same for equations. So Lee went on to say that math is timeless, pure thought, unchanging, and there's no place for observation or measurement. For instance, for the parabola was discovered purely from math manipulations, and it was only after the fact that it was applied to thrown objects. But if you're just thinking in terms of math and can use any math manipulation, that can lead to fantasies because you're not being tied to the physicality of the real world. And regarding time, this treatment of dynamic processes as static math objects was really the first step to spatialization and geometrization of time. Spatialization means treating time as though it were another spatial dimension. And that, that tendency was fully realized in relativity. Moving ahead a couple of centuries, we come to Newton. And his key constructs for time are absolute time and absolute predetermination. Regarding the latter, Newton said that, well, given the initial position of all particles and their initial velocity and the forces that exists, then everything is predetermined. So that view pictures everything really as a static whole. The universe had become timeless in Newton's model, an unchanging solution. Time was really replaced by computation. And again, well, these are these views. Basically, everyone I've read about this period says the same thing. Regarding absolute time, the model really pictures like there's some universal clock, maybe even outside the universe, that progresses at a consistent pace throughout the universe. It's independent of any observer and separate from absolute space. We jump forward 150 years or so to special relativity, which gets rid of time in physics in many ways. First of all, it replaces absolute time with relative to the observer time. And if you read the 1905 paper, it's very interesting that there's no attempt by Einstein to say, oh, here's the reasons with absolute time, and here's the benefits of going to relative to the observer time. And that is mostly true in terms of the physics community. You might assume that such a dramatic change in paradigm would be at least debated, or even if everyone instantly agreed, that they would enumerate all of the benefits of this change. But no, some peripheral comments, of course, but in general, no. We would just accept it. Furthermore, Einstein redefines time in terms of the speed of light and assumes that the speed of light is constant for all observers in all inertial frames, for both the speed of light approaching those observers and the speed of light receding from all those observers. And this is implemented into special relativity in the following way. If you're going to use special relativity in an inertial frame, you have to synchronize your clocks using Einsteinian synchronization, which goes like this. You send a signal from clock A to clock B, and that signal is sent back to clock A. When it gets to A notes the total time for that clock, for that round trip of light. It then divides that total time in half by assuming it takes the same amount of time to go from A to B as it does to have light go from B to A, regardless of the motion of that inertial frame. So if you do that, if you synchronize your clocks that way, regardless of physical reality, then you're guaranteed to measure the speed of light as being a constant c, whether that light wave is going away from A towards B or towards A from B. So the net result is that time equals the length of the path that it's traveled divided by c. Time is defined in terms of speed of light and assumes that the speed of light is constant for all inertial frames. The mathematician Hermann Minkowski, who had taught Einstein math in the past, showed that Einstein's special relativity equations were equivalent to Minkowski space-time diagrams. In these diagrams, we'll see that time can morph into space, and space can morph into time. So one selects a particular inertial frame and has the black axes representing the time and x direction in space. But for another frame that's moving with respect to the black frame, let's call it the blue frame, there's a different view of what's time and what's space. Those axes are rotated by the angle alpha shown here, which is a function of the relative velocity between the blue frame and the black frame. So time, which is multiplied by the speed of light to have it measured in terms of meters, just like the X frame. Time in one frame becomes space in another, and space in one frame becomes time in another. So if we shift and have the blue axis, now called the stationary frame, and the black axis is moving, of course, the same speed relative to the z-axis, then we have a mirror image of this picture showing how time of one morphs into the space of another and vice versa. Still another way that special relativity gets rid of time in physics is the construct of relative simultaneity. Each inertial frame or inertial observer has their own idiosyncratic view of what's simultaneous. For example, for some event X that A observes as being simultaneous with his present state, there will be another observer who sees X as simultaneous with an event in A's future, and a third observer who sees X as simultaneous with an event in A's past. Hence, in special relativity, there's no global past, present, future. Each observer has their own construct of past, present, future, and of what's simultaneous. Sometimes the picture helps. So we'll look at this admittedly crude diagram, and we have in special relativity, Maria's the observer, so her time axis is perfectly vertical and her space axis is perfectly horizontal. And she's at point A, which is 0 time and 0 distance on the horizontal axis. Now, event X happens on that horizontal axis, so Marie sees X, event X, as simultaneous with her current present. However, we have Freddie. Freddie is moving at some velocity with respect to Maria, so his time and space axes are rotated with respect to Maria's in special relativity. And B, Freddie is at event or location B in this space-time diagram, and Freddie sees X as being simultaneous with some point that's in Maria's future. So they have totally disagreements of, is X in the present or is X in the future, even within Maria's diagram. And of course, we could have another observer who sees event X as being in Maria's past. So everyone has a different view of past, present, and future. Lee continues, special relativity and general relativity gets rid of time. In the relativistic universe, it's like a timeless unity. The flow of time is an illusion. Relativity's reality is there's no global past, present, or future. All there is a four-dimensional space-time, which time is not separate from space. And that four-dimensional space-time is like a frozen block of ice. In special relativity's construct of space-time, in Einstein's words, space and time are subjective ways of dividing up a four-dimensional reality. In relativity, the universe is a mathematical, geometric object called by all the block universe view. General relativity is even more timeless than special relativity. It confirms the block universe view, and the construct of past, present, future only has local, observer-dependent meaning in the same sense as the terms here, left, right, and near describe location in space relative to an observer. General relativity is about the geometry of four-dimensional space-time, where the key construct is its 4D metric. And most interesting, and I think quite important, is that Einstein himself was distressed that the now, the present, in the sense of past and future, was absent from physics theory, and thought that this was a shortcoming, but in the context of relativity, saw no possible resolution. As a quick aside, I'll note that Lee brings out that quantum mechanics is also timeless and compatible with special relativity's relative simultaneity. However, the alternatives to quantum mechanics, such as the hidden variable theories of de Broglie and Bohm and Vigier, require absolute simultaneity. I had not known that before reading Lee's book, but I'd always had a preference for the alternative theories. They seem to be inherently more physical. Okay, on the theme of time has been removed from physics, or at least the essential properties of time, the past, present, future, simultaneity. We started off by saying there was a freezing of motion when it was transformed into a physics graph or into a static physics formula. This abstraction, with just a view of the math view, gave the picture of the entire process and no hint about its evolving through time. Next was the Newtonian view, which introduced predetermination, which seemed to be like a precursor to the block universe view. Next we had relativity introducing relative simultaneity, which meant that there's no global past, present, or future. It's all observer dependent. And finally there was the four-dimensional space-time block universe of general relativity, where space and time were welded together. Just to be clear, in case someone is thinking, I've been studying special relativity and a lot of its equations include T. Yes, that's true. T standing for proper time or observed time. But the point is that these points on this chart refer to special relativity's model, and in that model, some of the key properties of what we think about as being inherent in time, like the past, present, future, or simultaneity, have been removed from that special relativity model. Okay, we just summarized Lee's main thesis, namely that the properties of time have been removed from physics, and he considers that a problem. And further, the ultimate example of the essential properties of time being removed from physics is relativity. However, he goes on to say that he prefers relative time to absolute time. And he references Leibniz, who had his principle of sufficient reason. Leibniz said for questions like, why is the universe like this, there must be a rational answer. There must be a rational reason. So he looks at absolute time, and he gives the rhetorical question and answer, would it matter if the universe started 10 minutes later than it did? And Leibniz says, no. Therefore, time is not absolute. And Lee says, I accept Leibniz's reasoning. I would just comment that I think Lee was a little too quick and perhaps too inclined to accept a rationale for accepting the rationale over the absolute. Regarding that second bullet, I think it might prove that when you started the universe with time, might be relative. But using Newtonian thinking, whether you start the universe at x or x plus 10 minutes, if you use the same initial parameters, initial conditions, then you could have absolute time in both cases, just absolute with respect to whenever you started the universe. Just a thought. Since we're talking about absolute versus relative, we'll, as an aside, talk about motion. Lee makes the point, if motion is inherently relative, that does present a problem, another problem with relative, in that you can't assign any specific physical cause to that motion. And he further makes the point that geocentrism, which he dismisses as not good physics, rather Rube Goldberg-like model, it can only be justified based on relative motion. If all motion is relative, then you can take a Ptolemaic view of the world, even though the model is extraordinarily complex, and you have to add 55 adjustments for retrograde motion and have a rather convoluted explanation of the physics of what's going on and driving the motion of everything around the Earth. So there he concedes to strong arguments against physics viewing all motion as relative. In addition, I'll add my own view that I think there are good arguments that rotational motion and acceleration are absolute, because when you start the acceleration or rotational motion, you're introducing forces that weren't there before. So I extrapolate from that and say that when you accelerate from x to x plus 50, you're going from one absolute state to another absolute state of constant motion. Now we come to Lee's conclusion, and we'll also look at the challenge for Lee about that conclusion. Lee concludes that time has been removed from physics, as we've seen. But Lee concludes, but at least for certain areas, cosmology, quantum gravity, hidden variable versions of quantum mechanics, needs time. Physics needs time. But that conclusion presents a problem for Lee, because his belief system includes special relativity and general relativity, which are timeless. Lee's solution continues. He says we have to give up relative simultaneity and adopt a preferred global time and determine, at least for cosmology, the cosmological preferred state. And Lee further says, the fact that this contradicts the triumph of Einstein over the ether is a psychological barrier to taking the arguments for the reality of time seriously. And finally, he says, on a cosmological scale, preferred frame is valid, but on a smaller scale, relativity prevails. We'll now take a little bit of a deeper look at Lee's solution. He says, even on a cosmological scale, the preferred frame is determined by the actual distribution of matter and gravitational radiation, something that I would agree with. So it's not a throwback to Newton's absolute time. Yes, I'm in favor of absolute time versus relative time, but I do not want to go back to Newton's version of absolute time. So Lee continues, however, the day is saved by a new theory, shape dynamics, which gives the same results as general relativity. Now I'll give a few points to compare general relativity with shape dynamics. They both have limitations, but they're kind of complementary. In general relativity, simultaneity has meaning if two events are close, but as separation increases, the meaning of simultaneity decreases. However, in shape dynamics, comparing absolute size has meaning if two objects are physically close, but as separation increases, the meaning of absolute size decreases. So Lee keeps general relativity, but when Lee needs time to be meaningful, Lee just switches to shape dynamics. So Lee's solution, which we've just discussed, seems similar to what I've encountered many times. Namely, a relativist will claim that relativity is gospel, but he sees a problem in relativity and does an ad hoc fix to relativity. And then his view is relativity is correct, but the rest of the world is not understanding relativity correctly. They should be moving over to my modified version of relativity. Anyway, many relativists see the same problems in relativity, and there are quite a few different ones, and usually the relativists will see one out of many, and to focus on that one. They say the same problems in relativity that dissidents have articulated, but the two groups have different solutions. The relativists tend to patch with an ad hoc fix, whereas the dissidents / critical thinkers are inclined to take relativity to the landfill and come up with a totally different approach. So Lee's approach it strikes me as Rube Goldberg-like, by using relativity for some areas of physics, but when the properties of time are really needed, switching over to another theory. I just have the feeling that there must be a smoother solution. Okay, we'll wrap up part one with a summary of some key concepts that will be very important to understanding part two and part three. First, time has been slowly removed from physics, culminating in total removal from special and general relativity. And a few charts back, we gave some more detail to that, giving some specific examples. But despite this removal, Lee notes that certain areas of physics need time. For example, cosmology. But both Lee and Einstein and others can't find a way to put the essence of time back into relativity. And the final point is a general point. It's a quote from Lee saying, "Neither mathematical beauty nor agreement with experiment can guarantee that the ideas a theory is based on bear the slightest relation to reality." An important point for this series of talks and for all of physics. And it needs to be remembered if you want to be a critical thinker in physics. Before I go, I'll give you a quick preview of part two. It's a deep analysis of how special relativity evolved from Lorentz ether theory, yielding critical insights into relativity. And we'll do this through the lens of the construct of time that we've talked about in part one. If you're a critical thinker, your view of special relativity will be transformed forever.
People are waving at me because they can't hear me. It's my fault because I had myself on mute while I was typing. So I apologize. I'm sitting here talking away. My dad's waving to me, thinking I'm talking away. Sorry about that, everyone. They got to put it like right on the screen. That'll help me. I'll put that in there, suggestions for this. But I'm sorry about that. So Nick, are you there?
Yes. Can you
Okay.
hear me?
Yes, you couldn't hear
Okay.
me, and I'm sitting there blaming the whole rest of the world, sort of like relativity. But absolutely fascinating. We only had about 100,000 comments during that time, but many of them, especially in the beginning, is this is really the nerdy kind of stuff we people who like science like to talk about, because time is absolutely fascinating. So I just want to put something up here that if you want to. If you're in the chat, you can put in the chat either a question or a comment. We'll be able to bring that up. Of course, we have the green room as well. So if you want to come on live and talk here, you can. We have 10 spaces for you to be in the green room. I can bring you up and you can talk. You don't have to be on video. You can also just be on audio. But so there was a lot of different things I wrote down myself in questions. But I thought it was interesting how one of the things I really never thought of myself was how relativity just completely removed time. I mean, is it as simple to say that they took time and meshed it with space to make this mythical four dimensions, or how would you describe that to the average person? How relativity removed time completely?
Well, there are two aspects of it. One is just what you said. They made time in their model into another dimension of space with spatial characteristics, and but also because they based their theory on each and every observer's idiosyncratic view. That meant there were an infinite number of conflicting views of what's going on. Um, so that's how time disappeared. In fact, it sucked out almost all of physics by being so observer centric.
Yeah, I mean that's one of the problems. One of the things that I even got into any of this was with Dr. Riccardo Carosani, and the upshot of his work was basically there are no inertial frames. I mean, this
Yes,
idea that
right.
you have some, I mean, it's contradictory. It's contradictory to itself, right? I mean, if you have an inertial frame on everything that's moving, everything's moving in a sub. I mean, you look at anything in front of you. I've got something in front of me here that is going to be made of atoms, and each atom is moving. So, do you have an inertial frame for every one of those, and times different for? It gets it goes to the absurd level. Let me see. We do have a comment here. I think that was interesting about Smolin here. Let me put that up. It says you are this is just missing an interpretation of Smolin's argument. He only says time is removed because of the cosmological principle which he didn't adhere to. That is, the laws of nature don't change in time. Is that what you understood, or
No, no, no. If you read the book, it's pretty clear.
okay?
And in fact, almost all of those things are quotes from the book.
Okay. Why do you think a person may think this, that because of the cosmological
He
principle
may
that?
have heard Smolin talk in a different context.
Oh, okay. Okay. All righty. All right. Let's see here. Also, you did talk about time when it referred to the Big Bang. I know you didn't talk much about that, like the start of the universe being 10 minutes before or 10 minutes after. Was that just a generalized statement or a historical statement? I was sort of curious when you had mentioned that.
Yeah, that was in the context of Leibniz's rhetorical question and answer, which allegedly proved that everything is inherently relative, including time, which I think we'll see later is not valid. And I was trying to show the error in logic in that particular one, although Lee seemed to accept it.
Right, right. Okay, let's see if we have some other one. Questions. We have people in the green room. If you want to wave to me and talk about what you think about time or about the presentation, please say hello, wave your hand. If you want to come on, you can again go to live.naturalphilosophy.org. What that does is you got to put that into your browser. That'll bring you up here, and then you can come up and talk about it. Now,
Again, if possible, try to address the conceptual themes that I talked about because you know can't cover 2,000 years in detail, so some
oh
things
yeah, the problem is you can,
are
yeah,
left out. So but
yeah, you can easily get off track. Now, I think the first theme you talked about is how it's been slowly removed from physics. I think relativity seems to be. Do you see that historically as the extreme, the furthest
yes,
point we've
yes,
gotten?
yes,
Okay. And what, when people was, from what I kind of understand from that, the idea is then that mathematics also is culpable when it comes to removing time from physics, because what we end up doing is looking at it as a calculation. we look at it as an equation to predict something, but then somehow, how is that removing, just having an equation with time in it? Is that all? Do you, as a person who's thought way more than this about this than myself, is that also a problem? How could it be that just having mathematical equations that are useful, actually, like with space, going through space and sending objects into space, how is that also sort of removing time from the physical world?
Yeah, Lee said there were two problems with physics becoming too math oriented, because the math tended to shift the description of a dynamic process into a static math object. But he also said, and this was I did this quote twice, and it was the last bullet on that summary. He says that if you are working in the math world, then you can apply many, many different legitimate math operations. But if your model is not
The topic.
if the
Go ahead,
model
sorry.
is not constrained to some physical model, then you go off into a fantasy world with your math manipulations. And I think that happens a lot in physics.
Okay, so the summary concepts here, I'm bringing up your video,
Yeah.
is that time has been slowly removed from physics, and that's what we're talking about
Yeah, the
now.
third bullet was the quote from Lee.
Right, right.
Yeah.
Well, that third quote is pretty phenomenal in
Yeah.
general. I mean, if even though Lee is, he's probably off on a lot of things, maybe at the time when he was doing his work, it was, pushing a forward. But this has been repeated over and over and over. I mean, even Sabine Hossenfelder, who left the Large Hadron Collider to write a book entitled Lost in Math. I think, this observation has been very, how do you say, much seen by many people. And I also think that one of the reasons people are turning back to the newer models like Jeff Yee's model, like Borchert's model, like our particle model, are going back to a physical model where
Right.
you don't worry about relativity. You don't worry about what a person observes. Let's get to the point where we can even just say what we think light really is before we sit and talk about, transmission of and looking at events. Now,
Two examples of that quote are you started with special relativity and general relativity, which were built on a false assumption so that it didn't match the empirical data, but the academic world used math to create dark fudge factors like dark energy and dark matter, that they filled the universe with 95% of the universe with these dark fudge factors.
yeah, it's quite amazing. I think if you talk to the average person who likes science, I mean, I've talked to many people who they like science. When you ask them about dark matter and dark energy, that's one of the first things that comes out of the mouth. Yeah, when they don't know what it is, they just give it the word dark, and yet the community is so hell bent on that they get, I don't know, I think it's a giant distraction where I've even seen some of the science evangelists out there like Neil deGrasse Tyson saying that the person who discovers the next great Nobel Prize will be the finding of dark matter. And that is waiting to happen. That is just absolutely waiting to happen. Okay, I've got some other.
The problem is
Yeah.
they'll go and look at another galaxy and say, we see dark matter again, but all they're seeing is the dark fudge factor.
Okay, I've got some people waving in the green room, so I'm going to bring them up. I saw my dad waving. Hey, Dad, I saw you waving. Is that to say I'm doing something wrong, or did you actually have a statement there? I can't hear you. Can't hear you. I'm not hearing him. Okay, I'm going to bring him down. Let's get him his settings right. Get your settings right, Dad. We'll bring you back. Okay, I did see somebody else waving. I think it was James Keene. Yes? Okay, that's James Keene. Bring you up. James, how are you?
I am fine, and this was an excellent day for Dave and for Nick to present this. Put together some ideas while Nick was talking and would like to get his reaction. The ideas are: what if space and time are completely quantized? And we could make the analogy of the content of computer RAM is the state. In other words, each location is either a one or a zero. The clock of the computer is the time quanta. It is how often the state of the RAM is changed. And the program of the computer, and basically I'm making an analogy between the computer and the universe, okay? So the third and last item is the program, which during each clock tick of the computer is performing the time development of the state of the universe, changing which locations in space or in the RAM bits, um, uh, the time development laws is the program. So, and you have a cycling program, and that is the universe. Your turn.
Okay, I've in the past you have mentioned about quantization of space and time, and I really haven't had a lot of time to think about that particular aspect. But I will say in part 3, I give a physics construct to replace the general concept of time, and that just now thinking about it, it is quantized, but I don't know if it matches 100% your concept.
Well, wonderful. I like that response a lot. Guess I can't ask for more, except the big picture is that I have found here on in this forum and these broadcasts weekly that all of the dissidents, they all believe in continuous space time, and in other words, not well. There's some exception. Franklin, who thinks that space is quantized. You just conceded that perhaps time is quantized. So I'm wondering, my view is that the theory that time is continuous and space is continuous is an outdated superstition. End of story. Thank you. I'll sign off here and listen to your comments and give other people a chance to talk. Thank you.
Thanks, James. I love your stuff. Thank you. David?
Yes. Okay.
Okay.
I thought you were going to make some more comments
No.
there. All right. I've got Ian Cohen. Ian, how are you?
Hi,
Hello.
Ian.
Not too bad at all. Good to see both of you, gentlemen, Nick and David. I have a comment which Nick may wish to comment on in turn, and then maybe a more specific question. Excuse me. My comment is that the Minkowski type system, the coordinates they use, can be useful in classical physics, irrespective of SRT. So, if you have like x1, x2, x3, or the three spatial coordinates x, y, z, x4 can be ICT, the square root of minus 1 times c times time. And if you use that fourth coordinate, you get a sort of a generalized Laplacian where, the Laplacian equals 0. And in this case, you get the quad squared zero equals 0. So it's a useful system in classical physics. You can get the wave equation from that. Now, the more specific question was, this old chestnut about absolute motion. And you had one of the bullets there, Nick, where you said actually quite clearly that accelerative or rotational amounts to the same thing, motion was absolute. But I think you shied away from saying that ordinary linear motion was accelerative and was absolute. And I wonder what your view of that is, because you qualified the acceleration by saying, well, there are forces applying on that. And I'm wondering what your view would be on sort of linear relative motion, and whether you can actually attribute some sort of absoluteness to that or not.
Yes, I was arguing for absolute motion, and I brought up those two examples of acceleration and rotational motion. And then I said in the video, from that, I extrapolate to think of linear motion as being representing various different levels of absolute motion. So I apply absolute motion to linear motion as well.
Okay, so I think I understand now. But in a way, it's almost like the Cantor type, different types of infinity. One type of infinity is maybe more extreme than the other type of infinity. So in a way, unless I'm misunderstanding you, you're saying, well, the absoluteness of rotational motion is maybe more absolute than the absolute nature of linear motion.
Well, I just thought it was clearer that, or had a clearer argument that rotational and accelerated motion were relative. And I didn't have as strong an argument for linear, but I extrapolated from those types of motion to including linear motion as being absolute as well. And I think if you're doing physics, that's an essential view. But further, I don't go with the Newtonian view of absolute time, because the rate of time or its surrogates depends on the local configuration of mass and energy. There is no single universal clock that drives the entire universe ahead tick by tick. It's very much of the analog, or the surrogate for time is very much a local phenomenon and dependent on local physical reality. As Lee alluded to himself when he was talking about cosmological physics.
Well, to finish, I think I'll have to give a lot more thought to that, and I may come back to it with your permission for parts 2 and 3. Because I'm not convinced of that, particularly in regard to time difference. I'm not talking about maybe the starting time or the finishing time, because that can actually vary with physical circumstances. But as regards time difference, I do tend to use the Newtonian system. So I'm going to give a lot more thought to what you have just said, Nick, and we may come back to this. As I say, if that's
okay. I think part 3 will be, listen to part 3, and then we can continue this.
Okay, very well.
Yeah.
Thank you very much once again.
Thanks, Ian.
Okay, I'm sorry. I clicked on it this time, but I didn't click long enough on it. Gee whiz. Well, there may be some people that like it when I have it off, but I do want to thank Franklin Huey's showing you can make a donation, even if it's through Dissident Science. That money we put into the CMPS, so you can make donations online. You can also make donations, and I want to thank, we did get a donation during this talk. People are liking it, so we're going to have to bring you more, because you are lucratively important to us. But I thought here is really something, talking about continuity and discontinuity. I'm going to bring us up a little closer. This would be interesting because of my position of getting out there and supporting people, because my goal is not to say what's right or wrong. I just have this great empathy for anybody who goes out there and tries to think critically against the mainstream. That to me is huge already. And because of that, I often get books out of the blue, and this is one of them that is absolutely fascinating. I don't know if you can see the cover, but it says the discontinent continuity of motion. Now, where did this come from was even more interesting. I think this guy's in Canada, is from Canada, and he was a scientist, I think, in the 1950s. And what he did was he was into the motion of looking at high speed film. So he would look at things that were going to he could capture as movement. And there's another book that he sent I think his son sent, and basically what he was saying is, if you take where something is now and then move it a little bit further to where something else is, this whole thing of like this philosophical problem, like if you go halfway to a place, you'll never get there. But he really, after doing high-speed photography, where he captured literally, I don't know if he was part of the ones where you'd see a bullet going through, like, an apple or something at that time, way before we have the machinery we have now, which is much, much more capable. But it got him thinking that, is motion and time basically continuous, or is it discrete? What's your thoughts on that?
I haven't really tackled that in depth, but I think of time as being a physical process. So in that sense, it's perfectly natural to think of it as discontinuous.
Okay. Alrighty. So I know we have some people in there. I know Franklin Hugh popped in. Usually he doesn't do that by accident. So let's bring in Franklin. Hey, Franklin, how you doing?
Great.
Good to see you.
Nice
Hi,
talk.
Franklin.
Whoops.
Nope.
I got it. Wrong person. I'm
Okay.
Hi, Franklin.
Okay, I think we're having a little bit of technical problems. So, yeah, Nick, so I had some questions. Great talk. And yeah, I did make that $5 donation just to check it out. Although you can't do a super chat on the John Chappell channel. So, Dave, you might want to check that out.
that has to do with the number of subscribers.
Oh, does it?
So what you need to do, folks, and that's a good segue here, is please like and subscribe. It doesn't matter. It does matter. So I think when we get to 1,000, I'm not sure, 1,000 subscribers, we'll be able to receive super chats directly from YouTube. But you can still go to the donation side, which we actually get more that way because the YouTube obviously takes their cut. But yeah, that'll give you the explanation. But go ahead, Franklin. We're talking about time, and we're running out.
Yeah, so I had some questions on your presentation here, specifically when you showed that Maria chart and the two lines, and I just got completely lost about that. I mean, you seem to be trying to imply that people could observe perhaps a different sequence or something that someone observed in someone's past looks like it's in someone's future, which that completely lost me because I'm figuring that if you're observing something like, say, the moon, and you see rock A hit the moon, and then you see rock B hit the moon, I mean, that's a definite sequence of events which defines a definite past and present and an order of events. So, I mean, is that still true, or is it the difficulty here just that I absolutely don't believe in removing time or relativity of time, or that things could be observed in different orders? So, yeah, I was totally lost there. So, if you could try and clean that up.
Okay, I think because you're talking about two rocks hitting the moon, you're talking about two events that are relatively close. But the farther those events get replaced from one another, some people can see them in the past. The second one in the past, and you might be seeing the first one is simultaneous to your present state, but someone moving with respect to you will see the rock hitting the moon as being in the future of your time, because his view of space-time is distorted, It's
Well,
different.
I think you'll have to try
Different.
and explain that one sentence, because
Okay.
I don't see that being at all possible.
Oh, which part?
That someone could observe something happening, I don't know, in my future. I mean, or
He
past.
sees. All right. This is a Minkowski diagram, and Minkowski diagrams were supposed to be a direct graphical interpretation of Einstein's equations for special relativity. So here we have Maria at location A, and she sees event X as being simultaneous with her current position.
So
But
exactly what would that mean in terms of, like, what does that like put it in terms of the moon hitting the rock example? What would that mean for Maria? Is it like Maria sitting on the moon and she sees rock hit moon? What is that?
well, no, she's on Earth, and she's looking through a telescope, and she sees a rock hit the moon.
Okay, we can deal
So
with that. That's good.
So she sees, and she understands. She's not naive. She understands that it took so many seconds for the light to travel from the moon to the Earth and to her telescope. So, but for her view of the of space time, that hitting the rock was equivalent to her clock hitting 10 o'clock in the morning. But Freddie, who's traveling relative to that, to
So let's say
Maria,
Freddie
wait.
on
Let me.
Mars or something, right?
Freddie, who's traveling relative to Maria, we'll see that if the moon hits the rock simultaneous with, let's say, 12 o'clock noon in Maria's time, which is in the future of Maria at the time that she's looking at this in
Well, how
in
is
her
that
telescope.
possible? Because
That's right. How is it possible?
if
I
Freddie
think
is
your
looking at
question really is, how does relativity make sense? This is a portrait of the consequences of relative simultaneity. And I know a lot of people have the view that things are simultaneous or they're not simultaneous, and I kind of agree with that. I think there is a physical simultaneity, which I'll discuss in part 2 or 3. So I think it's not so much when I'm discussing special relativity, I'm not endorsing it. I'm just telling you this is the consequence of the special relativistic view, where all inertial observers' views are supposed to be equally valid physics, even though they contradict one another. And Lee was saying himself, this special relativity's consequences, it gets rid of an absolute or a global present, past, and future. Everything's relative to the observer. And I agree with you. It's difficult to
it may be my
agree with that
difficulty
view.
in understanding this, that it just seems completely absurd. I mean,
Yes.
if you take everything from observational standpoint,
Yes.
then I could say that I'm putting my fingers here and I'm squishing your head because your head has only become like half an inch, right? But that
well, that's perhaps a little extreme, but I agree with you. I understand your question and saying I have the same questions about relativity, but I'm presenting what relativity says, and not in my words, but in Lee Smolin, who loves relativity, but recognizes
your
the
point
same
is
problem.
Is that Lee is like the guy who put the planets around the sun, but not the Earth around the sun? Is that
I actually say that in part 2. I think that he has made a step in recognizing a problem. Relativity removes time from his physical view, or has everything as time relative to observers. And I'm saying that's a good first step. And the second step is to get, a theory that properly incorporates the essence of time. But he hasn't made that second step yet. Yes, I agree with you.
Yeah, although I
Franklin.
still would disagree with the concept that you're trying to remove time. I mean, I would say that that relativity is trying to move, I don't know, absolute time, but you cannot get rid of the concepts of past and, say, future, or the order of events, right? Because I'm thinking that, in the moon, rock A hits, then rock B hits. I mean, no matter who you are, no matter where you are, those will have to be observed in that order, which preserves past and future. Well, actually, I don't know. It doesn't really preserve past and future. I guess it preserves the order of events.
Yeah, I guess the problem with your example is that you tend to see them as pretty close together, but as you get further apart, no, you don't see them in the same order.
No, I think you would. I mean, no matter how far
According to
Not
relativity,
if you're a relativist.
if
Not
you're
if
caught,
a
you got to
relativist.
remember this is relativity, Franklin.
Yeah.
It's not a discussion of whether it's right or wrong.
Right.
It just
Well,
means
I
you
would
can come up.
challenge any relativist to show me an example. I mean, you could put trillions of years between events, and event A would still happen before event B by all observers, right? Not unless they
No.
can come up with a contradiction.
No, that's one of the problems with special relativity
Yeah.
is Lee, who's a great champion of relativity, admits and says explicitly.
Yeah. Okay.
So we're in agreement.
Yeah, we're in agreement.
Franklin.
It's a yeah, and we're not here really. I mean, I think the point is not to discuss how relativity screws that up and how, whether or not that's understandable. I think what the most important thing is to sort of give a historical concept of what's going on and just leave it at that, because it would be like taking illogical logic and then going back in time and say, okay, they believe this, and sit around with that model in your head and drive yourself crazy trying to find a corner in a round room. So I think that's kind of what we're getting here, though. Did you have any other comments?
It's important to determine whether Nick is, for example, correctly representing what Lee or the relativists are saying.
Right. So you have
dissidents. We put up straw men, and it's like, and then we attack that straw man, and then which may not have any reality
right.
to it.
Okay, so I understand. What I understand is you're in disagreement with the idea that in relativity you can't have a future happen at a different time from another person observing your and that's we can't solve that right here. So did you have any more other comments, or was that pretty much your question?
No, yeah, because I was just confused about what the heck that meant, and perhaps my confusion is due to my complete inability to dismiss logic. So,
well, that's what, and we both agree with you because special relativity, even in parts of general relativity, it's just not logical. So what can you do? So you're right.
I can assure you, Franklin, that my representation, really Lee's representation that I presented, is held by relativists and is in the textbooks over and over again and very explicit. And that's why so many people have reactions like you.
That doesn't make sense. Still doesn't make sense. Every single time I see stuff like that,
I know, but again, what we don't want to do is sit here and go back in time and discuss, for instance, this is just sort of like the same discussion as to say, what kind of mechanical way, I don't know if anybody's seen these clocks from like the 15th century where you have, it traces out the paths of the planets, which do like S kind of patterns. Yeah, we can discuss, that whole model and how you make that and how complicated, and it's just not, or we can say, yeah, that's the way they did it. It doesn't make sense. It's a lot harder, and just move on. So
yeah,
I understand.
I think Franklin will like my parts 2 and 3 because I'm of the same mind, and will be saying, hey, this taking time out of physics leads to a lot of contradictions.
Yeah.
And
see, well, we'll see. So
common sense.
My personal opinion is that time is quantized, that there is an actual global universal, say, clock that everything moves by, is my personal opinion.
Yeah. Okay. All righty. We will. Let's go on. I think. Thank you very much. And I think there's somebody here. Of course, we're going to have people that disagree here. Let me see here. There was something here. Time is a relative construct based on the time of clock. Here. This was a comment, I think. Again, we're discussing the history more, which is okay. I mean, this is discussion of history. He says Franklin is right. Special relativity preserves cause and effect. Some fundamental flaws in understanding of relativity are relativity on display here. So
let me say that again. Lee was very explicit about that, and I had that as one of the points in my summary. That, as he said, the relativistic view, the observer-centric view,
right,
does remove cause and effect. Now, the nearer things happen, and the nearer the observer is to what's going on physically, the better he can discuss cause and effects. But there are limits to that in special relativity and general relativity.
right,
and it's admitted by the relativists. It's,
right,
it's not a
right.
controversial point.
Yeah, I think part of it is that people, you see when you're looking at something as absurdly complicated, really it is, as relativity, especially special relativity, it's so absurdly complicated, is that it's really tough to stand back far enough to come up with a conclusion where that time is no longer part of that. I think when again we get into the minutia of our interpretation of an absurd theory and concept, and we get caught up in that when we say, okay, like you're saying, look, me too. I mean, we can think ourselves into a corner trying to understand this. And I think one of the problems is that if we don't get past it, we're not going to get to another solution, or at least move science forward. So it is complicated. I mean, the moment you try to think of all, like I said, here you go, put an inertial frame on every moving thing and realize that every moving thing's made of atoms, and those are made of moving things, and there's electrons going around the nucleus, and those are moving. And then go calculate all the calculations you need in special relativity to find out the relationships of cause and effect. It's just, in fact, in my documentary movie, Dr. Peter Marquardt says that was the problem of it. It's not relativity is not a theory about events. It doesn't care about the event. It cares about the observation. So it's quite interesting. Okay.
Yeah, let me make just one final comment to Kev.
Sure, absolutely.
For him to think about special relativity says that every inertial observer's view is equally valid regarding the physics of what's going on. But all of these different views are contradictory and different than one another. So in that context, you can't really define cause and effect. You can if two observers are standing right near each other, but the farther they get separated, the more distortion as to their view, and the more difference their views are about cause and effect. And I will go into a rather detail on that in part 2.
Okay, we do have a question. Again, if you want a question or comment, if you do that, I will put it up here. Here's a question from Alistar Riddock for Nick. Would you consider what it would mean if the fundamental components of existence, whatever that may be, are immutable, thus unchanging and eternally existent? Trying to figure out.
I don't have any problem with that view. I think there's a lot of evidence that over a long enough period of time, everything changes. But I don't have any problem with people thinking about things being immutable or unchanging or eternally existent.
Okay.
I think Alistair Rudick had another point in the chat that I thought was interesting. But
oh, okay. Well, do you remember which
know.
one? Let me see. If you, let me see here. Okay. Do we have people in the green room? We have anybody else? We have Jim Marison is in there. I think he's in there. But I think we've talked to everybody there. So let me see if we have some more. I do have, let's see, how much time do we have left? We have 15 minutes.
Let's see, Alistair, if you made
Yes.
another point that we haven't discussed, why don't you repeat it so it'll come to the end of the chat?
Yes.
We might be able to see it.
Yeah, that would be fine. I do normally star them. We have them star. But I see Jim Marison. Did you want to come up and say something? I know you worked yourself way in here, so I'm going to bring him up here. I'll be looking for the other guy. Go ahead, Jim. Are you there?
Hey, can you hear me?
Absolutely. Great to hear. It's great to see you, Jim. Welcome.
Right, thank you. Yeah, I guess for people that study this kind of thing, the biggest problem is the Michelson-Morley type experiments. Wondered if you wanted to comment more about that, and I have some of my own comments.
That's how I start our part 2 with the
Okay.
Michelson-Morley experiment and the effects of that.
Because that's really what led to this wacky thoughts about time.
Yes. I will talk about that in depth. Yeah.
All right,
Part
so I just want to point out that there was an experiment in 1979 that that may have actually found a positive result for the Michelson-Morley type experiment they did. I did with John Hall. Are you familiar with that?
Does that show motion with respect to the constellation Leo?
No, it was
Okay.
looking for that. That's the problem, because
Oh, okay.
it detected a possible motion of the laboratory with respect to the ECI. But
Oh, yeah. The laboratory does move with respect to the ECI, because the ECI is the Earth-centered inertial frame without rotation, and of course the lab rotates with the Earth. Yeah, the Earth's surface.
yeah, and the Michelson-Gale experiment detected that.
Yeah,
as a first order phenomenon, but the Michelson-Morley experiment, second order, and it's much more difficult to detect that
right.
that velocity because it's so small. I guess I'm not explaining myself very well, but the point is that if a first order experiment can detect it, and ring lasers detect it every day, why not second order? And the problem is that none of the experiments that have been done recently that have the possibility to detect that have actually looked for that motion. And
Good point.
And that the best way to actually find it perhaps would be to repeat the Michelson-Morley experiment in outer space, in orbit, local Earth orbit, or even better, in interplanetary orbit.
Right.
So,
good point.
So that's what we need to do.
Okay. Do you have any more comments or
and then
questions?
that would solve all the relativity stuff.
Yeah, I think so.
Okay. Any more comments?
Well, I'm glad you
Jim?
agree.
Yeah.
So basically, I guess you're saying that we're going to be talking about that. That's an interesting point. I know I've asked you several times about are you an etherist or not, and you talk about it. You've studied it. You've looked at it in comparison to time historically. But I haven't, even in your bio you talk about it. Is that more of a historical factor, or is that something that you yourself adhere to?
Are we talking about ether?
Ether, yeah, ether, because
Okay.
I do know that, how do you say, as Jim points out, and you're going to be talking about in your second talk, which is a good sort of segue, that I was just curious on your point, because I've asked you a number of times. You said, well, I'm not either way, but you look at it more historical. Has it been more historical for you? Do you have any ideas, or that's
Yes.
just,
Yeah.
go ahead.
Um, I believe that physics needs a preferred frame for measuring motion and for measuring how motion affects the rate of atomic processes. So I'm in common with Lorentz ether theory in that that's a preferred frame theory where the preferred frame is the ether rest frame. I haven't seen enough, detailed data about what the preferred frame is other than it's the GCI frame in the locale of the Earth. So I am a preferred frame backer, strong backer, and that's compatible with ether theory.
Mhm.
But
Right.
I don't see any empirical evidence to say that that preferred frame must be the ether.
Okay, I got you. Okay,
When
that makes more sense. Yeah.
I do have some, I think, brand new ideas that I will bring to the ether debate, whether that you talked about earlier.
Yeah. Oh, good. Well, then I'll bring you in because that it's going to be, it is interesting to me because I think, until, for instance, I guess there's lattice theories. I don't know anybody who's really developed that a lot. Believe it or not, who was sort of a proponent of lattice theory was Ron Hatch. Ron
Mm,
Hatch with the GPS. He had this real feeling. I asked him, I said, I think, there's this kind of lattice in the universe. And that, sort of was, how do you say, satisfying to him as to look at this preferred frame or idea there, especially with GPS. He had over 30 patents in GPS.
right.
And then, of course, one of my contentions is the reason people look at ether is because they look at light. Light looks like a wave, it acts like a particle, but people are just can't get away from the wave aspect. We see an ether medium could be an explanation for that, and that's where they land. Although there are at least three different models out there. So okay, so your contention is yes, there is some universal thing out, some universal frame, sort of like I guess Karazani said, and I read his work, his mathematical work for a number of years until I came to the conclusion that what he was saying is you can't have more than one frame. All you can do is move the origin from which you measure, and I think it's kind of in the same vein. So
Yeah,
that's
I use frame as a shorthand to talk about, but it's motion with respect to some other physical entity
yes,
that's
yes,
key. But that
yes,
means that the preferred frame is as a local reality, and if you're
yes.
on Jupiter, it might be the JCI frame. That's the preferred frame in the locale of
Well,
Jupiter.
right, and even the
Yeah.
perception. I mean, one of the things is even with life forms, we can see it. That is, the bigger a life form is in our local world, it
Hmm.
seems that slow time is a different.
Yeah.
Seems you look at ants; they're moving at an incredible speed, and I mean it seems trivial, but in some sense you can see that I know that my father and I talk about time, and one of the things we say when people ask us about it, I say it's sort of a kind of an invention we use to be able to describe motion and make predictions of things about motion, really. That's what it's about. Whether or not that thing is there, that you can point to it, but it's certainly tied to motion quite a bit. So I think that's
I addressed that in part 3.
part three. There you go. I mean, this is great. I mean, I didn't, you really know you're an uber nerd when this is just like really great. This has been a very popular presentation. We have about 7 minutes left. Now, I'm going to ask you because I know you've been doing these talks and things, but you yourself, when you were looking at this task to look at really the history of time, it seems to be really related. This is sort of a meta thing, so we don't have to get into anything, but it seems to be inextricably linked to relativity. Is that more of a historical thing, or if someone didn't come along and come up with this idea of time dilation and all this stuff, would that have happened, or is it just a historical artifact from the human race that we had an Einstein come along and do this and sort of got us off track in some sense?
Well, in part two, I go into depth about the transition from Lorentz ether theory to relativity. And it was not a historical necessity. It could have been skipped over.
So what you're saying is, if I saw this on Einstein's Facebook page, it says, "What if Einstein didn't exist?" Of course, my comment was, "Oh, we would have advanced so much further in science
Yes.
if and that's not what they were expecting." But so you basically, if I understand your answer, is this is
Yes.
a historical artifact that has really thrown these monkey wrenches in so that people like Franklin Hugh, myself, yourself, sit there and try to understand this when we get it into college and we get this course on special relativity, and it's really been a distraction. So
Yeah, my view is from a historical point of view, there was a natural progression, and then Einstein came along and without any real rationale for doing it, as I alluded to earlier, went down a dead-end street. And now we have to come back to where he made this wrong turn, and then we can now make progress. That's my historical view.
okay. Yeah, that's mine. I think there's a lot of people in that question. If he wasn't around, how much time, where would we have been? Where could we be in the future? So again, we'll be talking summary wise. We're going to be getting 2 more talks. It won't be next week, folks. We do have Lynn Tao next week, but the week after we'll be getting the 2 weeks from today. We'll be getting the talk, the second talk. Why don't you give one more time summary for those maybe who just joined, what you're going to be talking about 2 weeks from today?
Okay, we'll talk about how MMX, the Michelson-Morley experiment, forced Lorentz to make 3 changes to Lorentz ether theory to coincide with the alleged findings of the Michelson-Morley experiment. And what Einstein really did was to just flip those 3 things on its head without any justification to go down a dead-end street.
Okay, all righty. Well, listen, I want to thank you first of all. It's not easy. I've asked numbers of people in certain areas, expansion tectonics is one of them, and I have people writing books on the history of those things, and they say that's just too big of an endeavor to do, and to look through all of history and put down sort of a new evolving, as we say in our talk or in our title of these series, an evolving view of the history of science. It's not an easy endeavor, but I do want to thank you greatly. I do want to put up here for everyone to, again, please support everyone. Support Nick. Nick has a YouTube channel. This talk he has will be on that YouTube channel. He's got a lot of videos. I've watched them all. They're really great. We make sure you subscribe to them, that you like the videos. In fact, if you're watching this, please click the like. Why? Well, more people will come in this direction because I do greatly appreciate everybody's support. And thank you, Nick, so much for this talk. I mean, I know there's a lot of questions that we probably didn't get to, but maybe someday we'll get enough money, we'll have production people.
And I have to thank Lee Smolin for his
Yes.
excellent book, and he is definitely a critical thinker. I just
Yes, he is.
needed him about
Oh yeah, absolutely. And
being
it didn't
tightly
he?
bound to relativity.
Yeah, didn't he write also Stephen Hawking's "Smoking My Socks" or something like that?
I guess so. I don't remember that specific.
Yeah, I think it was a very strange book, but if you look him up, yeah. But absolutely, he's a critical thinker, and it's just
Yeah.
I know lots of critical thinkers that I think myself are going to go down in history, but for one reason or other on another topic in critical thinking, they're pretty much mainstream. So again, I want to thank you so much, Nick, for your time and your efforts, and we're really looking forward to those future talks. Remember, folks, nick.naturalphilosophy.org, go to his website, and we'll see you in 2 weeks here, and I thank you so much.
Thank you, Dave.
All right. So again, please support him, nick.naturalphilosophy.org. That's not his web address. It will get you there. It's a shortcut called the subdomain shortcut that will get you there. So greatly appreciate it. And I do want to thank everybody. If you want to make a donation, you can. Someone says it's hard. It isn't that hard. If you're used to the internet, you can go to membership.naturalphilosophy.org, click on one button and just fill in your information. You can take a credit card. I think you even do bank accounts depending on what it is. You can also become a member. That's very important. It's very vital to this. You're not going to find anything like this anywhere, nowhere. So I want to thank everybody for their support, and we're going to head on our way out. And remember, next week, folks, it's going to be 3 hours later. The good thing is, if you haven't, go to naturalphilosophy.org. If you go there, let's see here, we'll go to the website. Here we go. If you go to naturalphilosophy.org, they're right at the top right-hand corner. There's a subscribe. Put in your email. We do emails twice a week for these talks, and we even send you a link that will tell you right what time it happens in your part of the world. So you do want to subscribe to that, and you'll get more information. You'll be more alerted to when this happens. You can also simply subscribe to our YouTube channels and hit on that little bell, and that little bell there will tell you when we go live. I get it on my watch, and I go, oh, it's time. So thank you so much. I hope you've really enjoyed this. This has really been a great day. And let's take it all the way out and on our way and close this down. Yeah, I know my hair's gray. I got to update those things. But remember, like I say, always say, stay critical, stay thinking. I'm Dave D. Hills, your science therapist, trying to get you the promised land of becoming a critical thinker. Ciao for now.